Well, hello, friends. Welcome back to Browser Hacking. Today, we are going to try something a little bit new in Ladybird. So, I've been looking at some of the WPT tests, and we have this issue that they take quite a long time to run, especially the ones that have a lot of subtests. So, I've been kind of profiling and looking for ways to make them go faster. And I had this idea today that I wanted to try, but I figured I would start recording so that I can try it in a video. Maybe it will be interesting. So let me show you the issue. I'll just grab a test here that has like 4,877 subtests. So apparently it took 1.4 seconds for Ladybird to run this test. And let me try to run it locally in Ladybird. We'll see. Actually, seems to take way more than 1.4 seconds here. Yeah. Okay, so it's still going, apparently. Okay, yeah, so that took quite a while. So there are just tons of these tests in WPT that take a long time to run. And there are a couple of different things that we've done already to try to make them go faster. But let me profile this thing and I'll show you something I thought was interesting. Let's see. Let's just make sure that we have this, and we'll just start a fresh browser instance, connect instrument, run the test. Okay, now we're profiling. You can see that it's just very, very busy here, right? Just pure CPU churn going on. And then we're done. Okay, yeah, and the sausage stops growing. So let's select out the actually active part here. Wait, am I even selecting? Okay, there we go. And then we'll drill into the main thread, sort by top functions. Here we go. Okay, so we can see that there's a bunch of different things going on. There is, you have to sort of skip over all of these things here that are just like ways that we run JavaScript, because you can see that there's no self-wait in any of these things. So they're just like calling functions that are in every stack. But you get kind of used to that when you look at these profiles. So we see here, layout is one thing. So we have like 18% in layout. We have string replace, 18%. String split, 12%. And yeah, regex execution. But, oh yeah, you can see the garbage collector here also sitting at 8.5%. But the thing that I wanted to look at is this guy right here, regex prototype flags. So at 6.1%, that struck me as a bit strange. Like, why is that so heavy? Because regex prototype flags, that's when you do dot flags on a regex, right? So we'll just create a regex. And then we will put a G flag on it for global search or whatever. And then if I do that, it should print out G, I think. Yes. So this function is apparently very heavy. And if we open it up, we can see that basically most of that heaviness is an object get. So if we look at the source code for how we've implemented regex prototype flags, we can see that there is this whole thing going on here. Actually, it's done as a macro. But if we look at what the macro is doing, we can see that it's for every flag that we know about. Here's a list of all the flags. It's one of those X macros. For each one of these flags, we will do a get on the regex object with the flag name as the property name, and then convert that to a Boolean. If it is true, we will append a corresponding character to our output string and then return sort of the output string. So if you have the, I think we can see them in the macro here. So if you have like the global flag set like I had, you'll get a G in the output string. If you have the ignore case flag, you'll get an I in the output string, and so on. And these object gets here are what we end up spending so much time on in this profile. And it's kind of unfortunate whenever we do a get in C++, because when we do a get in JavaScript code, we have inline caches. So we can remember the next time you call the same function that does a get, we will remember where we found that property, because we'll do this shape-based inline caching, like all JavaScript engines or all mature JavaScript engines do this, and that allows the get operation to be really fast. But when we do a get in C++, we don't have the benefit of an inline cache, so we have to do a sort of full property lookup every time, where we go and sift through the object property storage, and if we don't find it, we have to look in the prototype chain and all of that jazz, right? Which we don't have to do in JavaScript. So where am I going with this? Well, I thought, what if we rewrite this function in JavaScript? And then we would get the benefit of caching all these gets, which could potentially be a lot faster than what we're doing here. And it would also, if it does pan out and it is faster, it kind of opens up an interesting door, right? Where we could potentially implement parts of our JavaScript engine in JavaScript and actually get a performance boost from it if it does work out. So that's sort of what I wanted to mess with today. And we're just gonna hack this together. So this might not become like the most beautiful thing. I just want to test it out and see how it goes. And I guess we'll start by just making a little quick test here. We can put this guy in a loop. I'll do it 10 million times, let's say. We have the regex, and then we're just going to say, like, we're just going to do dot flags on it, right? So how would that go today? Okay, that takes quite some time. Maybe a little too much time. Okay, what if we just do 100,000 of them? Okay, well, maybe 1 million was okay. Right, so we're looking at about 680, 700, 660 milliseconds on average. Cool. So let's see how we would do this in JavaScript. I guess the first thing I would want to do is just go look at the spec to make sure that that there isn't anything crazy here that we couldn't just do in JavaScript. It's an accessor property. Sure, so it's not a function, but an accessor. That's fine. The set accessor is undefined. Its get accessor performs the following steps. Okay, so we have a this value. If this is not an object, throw type error, sure. And then code units is an empty list. And then we start doing these gets here. So like do a get of hash indices, do a get of global, do a get of ignore case. And then we're appending to code units. And in the end, we return code units as a string. Okay, so how would I write this in JavaScript if I were to write this in JavaScript? Something like regex prototype.js, let's say. Okay. And then maybe I would call this regex prototype flags, just like this. Okay. And let's just go step by step, like we were writing C++. This feels redundant, but let's just roll with it for now. Okay, I don't need to copy the number. If R is not an object, throw a type error exception. So I guess, yeah, exactly. This is how I would have to do it. Do a type of object. This one already feels like it's going to be a performance issue, which I'm sure we can work around somehow. Okay, I need to stop typing the numbers. Code units is an empty list, so I'm just going to go with an empty string here. And then, let's see, has indices. So if we copy those two, and then something like if r.has indices, then code units, we append D. Okay. Yeah, so this is kind of what I'm getting at, is that if we can get away with doing this, then this get right here will be cached. And as long as we're calling this function or invoking this get accessor with a regex object that has the same shape that we've seen before, we will remember where has indices is stored in that object. So I think okay, maybe I'll just copy all these guys. Thank you, Copilot. Okay. And then the final step was to return the string value, yada, yada, yada. Which for us is just return code units, right? Okay. Okay. So how do we install this thing on the prototype? I guess, where do we set the flags thing? It will be somewhere up top usually. Here, define native accessor flags. Right, so for this is just a string right here. For the property name flags, we have the getter flags and the setter, there's no setter, it's undefined. So I'm thinking define native accessor in JavaScript. So flags source, flags JS source, I don't know. Something like that. So we'll invent a new thing. Native accessor. So it'll be similar to what we already have, except instead of taking the getter as a function object, we will take the getter as a string. String view, maybe even. Getter source. And the setter also. Okay. Define native accessor in JS. And then it has to do kind of what this function does, except in JavaScript. So we have to parse and compile and all that jazz. So we should have all the things we need to do that. Just have to find them. Okay, so let's see. If getter source is non-empty, then we should here create a getter function somehow. Same thing for the setter source. Okay. We're not going to do a setter right now, so I'll just leave that as a to-do. And I don't want to create a native function. I want to parse this thing. So I think we just start by like making a lexer of getter source and then a parser over the lexer. Is that it? Is it that simple? No? What do I need to say? Probably just need to include it. Parser, it's not part of the runtime, it's just there. Okay, sure. Okay, and then do I just parse it? I guess this is kind of similar to when you construct a function object from a string. So if we look in function constructor, we have like create dynamic function, which is that the thing I'm looking for? No, I want the one that constructs from a string. Body parser. Oh wait, this one does deal with a string. Body arg. Oh, you do pass an arg to this guy. So maybe this is what I'm thinking of. Okay, so what is he doing for the body? Body string, yada, 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 sure. Where do you parse this? Body parser. Parse function body from string. Is that the thing that I want to do? Body string. And then if you have errors, then you throw. But like we shouldn't have any errors because these are going to be sort of compile time JavaScript or whatever. So what was the format of the body string? It is... Wait, what? What is the prefix? Prefix is either function or async function or function star or whatever. Okay, so essentially we want to do like function, name of the function. So it should just look like a function. Actually, like it already does, basically. Okay, we're just gonna ignore the future where we might want to have multiple functions in this file because this feels like the input to parse function body from string or whatever it was called. So what if we just function is parser, parse function body from string, yes. And we want to parse that from the getter source. Wait. Oh, wait, then how is this used again? Gives me a parser. Wait, this thing is so confusing. It's just like, it's only used here to parse it. And then we do a second parser. So we parse twice. Oh, wait, what does it say here? The parameters and body are parsed separately. Okay, so it looks to me like we're actually parsing twice for some reason when doing this. So maybe I don't need that. Maybe I just need this second thing here. I just want to parse a function node and get a function expression back. That sounds reasonable. Can I do this? Is that going to give me what I want? Well, I guess we'll find out. And then how do I turn that into a function? So I have to check for errors. And then I create an ECMAScript function object from the guy. Okay. Let's try that. So should verify that parser does not have errors, because that would be, compile time. Or that would be a mistake that I should have prevented at compile time. Sure. Maybe we'll name it like property key to string or whatever. Can use that as the name of it. There's a lot of stuff here that I don't have. Source text. Prototypes. I wonder, is there a better example that I could use? Hmm. Maybe this is what I need to be doing, like getting the prototype here. Okay, let's try. I mean, what's the prototype of this? It's just a function prototype. Um, or wait, is this thing? No, it's not receiving a prototype. Right, okay. Realm, intrinsics, function, prototype. There we go. Okay. The source text is the getter source. And it's calling this expr, so I'll just call it expr. The environment, we don't have a private environment. The environment is going to be the global environment, I think. So let's just say the environment is the realm global environment. Okay. It's not going to compile. I just want to find out what I'm missing here. Also, CLion is not complaining, which is suspicious, because I feel like I'm definitely doing something wrong. Like there was something called parsing insights that I never defined. So let's look at that. Parsing insights. So where did we get that from in the function constructor? Parsing insights. Well, what if I don't have that? Can I just say like I don't have it? Will that work? No. Okay. Well. Okay. So now CLion is waking up. No matching call for create. Environment. Oh, I probably need to include the global environment header. Could that be it? Not quite. Global environment star star. Oops. Did I ampersand something that I shouldn't have? Okay. Undeclared identifier flags.js source. Okay. So that's this guy right here. So I'm just going to copy paste my JavaScript code into this file. Oh my goodness, that was a little bit messy. How can I get it in here looking good? Let's do that raw string thing. I always forget the syntax for raw strings in C++. So I want to do like this, and then it ends with the corresponding trailing thing, whatever that is. Is that how you do it? I'm messing it up. What the hell is the ending? This is the ending. Okay, there we go. Was that not how we did that? Right. So that's not a string view, but we add SV and it becomes a string view. Okay. Okay. So that crashes. Sure. It crashes in toString without side effects. Okay. But it does run. And if I run with like dash D to dump bytecode, we can see that it actually has compiled a function called flags. And we're trying to run it. So that's really interesting. I wonder why toString without side effects is failing. So value CPP 353. Verify not reached. Okay, so we are trying to print out a value that is none of these things. Or we're trying to stringify, rather. Okay, so let me run this in LLDB. Or actually, I've been trying to use the C-line debugger a bit more. So let's see if we can... Oh man, how do I run this with arguments? Run debug JS. Probably a way to do this. That's not at all what I wanted. Edit configuration, no? JS. Program arguments. Okay, so re.js. And I'll just put myself in this working directory. Okay, we'll stop and we will debug again. No. Oh, maybe I can't use tilde in paths here. Um, okay. So we're trapping in type of. Oh, interesting. Okay. Type of. So I was using type of in the code. Okay, so we're not getting the correct this value, I guess. That's interesting. So what should be the this value when you invoke this guy? It should be the prototype that we're, I mean, it should be the regex object that we're being called on. So why would that be empty here? Or why would it be an invalid value? That's kind of suspicious. I mean, it's probably something related to how I set this thing up. So the environment is the global environment for the realm. Function prototype, sure. I'm just splitting these up so that I can see what the hell is going on. There's too many parameters to this function. What was this null pointer here? That was the private environment, I think. That's strange. So this value is no good. So is it, what if I just log this here? Let's do this and then okay, so it prints out R and then we have an empty value, which we're not supposed to be having. So this is wrong here. And why is that? Am I using the wrong, I mean, what environment should I use to get the right this value? Maybe I have to inform it that it's using this thing. Because this is a bit jank that I'm sort of providing parsing insights that are not my own. So I have this insight. Wait, where do I get the parsing insights from? I can get them from a function node. Oh, wait. So I don't want to make my own. I just want to get them from the expert parsing insights. Oh. So it could be that was confusing something. Yes, it was. Okay. So we have this thing called parsing insights, which is like metadata that the parser collects. And one parsing insight is like, does this function ever reference this value? And if there's no reference to it, then we can take some shortcuts and we don't have to actually materialize a valid this value because nobody's going to look for it anyway. And yeah, so that was default initialized to false. And what I should be doing is just taking whatever insights the parser actually gathered. That's what I should be using here. So that makes sense. So that means that this thing is now runnable. Okay. And if we throw it to hyperfine, it's actually quite a bit faster, right? Because the one we had before was like 660, and this one runs in 477. Now, will it pass pass all of our tests? It seems like it does. That's very interesting. Okay. So let's put like more flags on there. GU. What are the flags? I don't actually remember them. We had D. Yeah, let's do like the worst case scenario where you have like every flag. So DGIMSVUY. Okay, that doesn't sound good. U is incompatible with V. Okay. Well, shows what I know. Okay, there we go. So now we are using a bunch of flags, and it takes about 900 milliseconds to do all of these. And if we just git stash, compile master, instead of 900, it would take... Okay, I'm just going to... The first run is always tainted because on macOS, like it has to do some shenanigans to whatever it is that it does. Like the first time you run a newly compiled executable, it's something related to code signing. Okay, so it's actually a little bit slower here, it seems like in the worst case. 800 something. 850. Yeah, okay. And the new version. It's a little bit slower in the new version. Not much, but a little bit. Oh, and I'm probably tainting. Okay, actually, it's tainted by sea lion hogging a bunch of CPU and stuff, of course. So an obvious thing we can do here to make this faster is to just be a little bit less verbose. So if we look at the bytecode that gets output for the flags thing that we wrote, we can see that it starts by moving this value into a local temporary register. And we can just not do that. So instead of having an actual thing called R, we can just say if type of this is not object. And that gives us a little bit less to do. And then, of course, we have to change all of these R as well. Oops. This, sure. But if we do that, then our bytecode is a little bit shorter because it starts immediately with the type of. Okay, and does that make it go any faster? It actually does. That was already enough to put us at speed parity with the C++ version. So that's interesting. Let's just verify that. So 809. There's some hyperfine argument to like do a warm up, I think, to throw away the first one. Yeah, there we go. Oh, okay, dang it. It's even faster. Okay. So we're still have to do some stuff to catch up. But it is interesting that it's not that much slower. So next thing I'm looking at is this guy right here, which this is definitely a clunky operation, right? Because like we do a type of, and then we compare it against a string and do all this stuff. And that feels like something that wants to be sort of an intrinsic, I guess, like a compiler intrinsic. Yeah, because you have to do a type of and then a jump, and then you have to do all this stuff, and then here we continue. And all of this initial stuff here, it really wants to be like like a GCC built-in or whatever. So let's see, how would I write this? So this is actually, now I'm editing my JS file, not the copy-pasted JS file that I have here. So, okay, but what I really want to do is I just want to consolidate this into, what do we do in the C++ today? Here, we have this object helper. Sure. Right, so we have a helper that will do an object check on the value, throw if it's not an object, otherwise return it as an object. Right, so I think, do we call that require object coercible? No, that's not the same thing. It has to be an object. Throw if not object. Yes, we have a bytecode op for that. So that's what I want to do. I want to emit this thing. So something like this, maybe? I don't think at is allowed in function names in JavaScript, right? So we could use that for this. That's not allowed, is it? No. Okay. So what if we allow ourselves this little treat, and then we wouldn't have to do this. And instead we would do something like this. Okay. And how do we make this generate that? We need to put the parser in a special mode, I guess. So parser, I guess Alexer needs to be in a special mode because it has to allow internal identifier, let's say. We're just going to hack this. So I will add a field to the Lexer. Allow internal identifiers. False by default, sure. Okay. And then when we're checking if something is the start of an identifier, we can say, I guess we can say if code point is add, or if allow internal identifiers and code point is add, then return code point. Okay. Okay, so now that, oh, right, I didn't edit it in the C++. Okay, so throw if not object, this. Okay, right, so add throw if not object is not defined. But we're making progress here. So now it's trying to call that function. And I don't want to do that, actually. I want to hack the bytecode generator so that when we try to do a call expression generate bytecode. Yes, this guy. When we are calling, so we're calling an identifier. I'm going to look right here. This is going to be my little cheat spot. If identifier string, let's just go right at it. Throw if not object. Yes, this is very hackish, but it's just in the interest of plowing ahead. So in this case, we're just going to do exactly this, where we just emit the throw if not object bytecode directly. And then we're done, essentially. Okay, so how would this end up looking in the bytecode now? Right, so now we've consolidated that whole type of string compare into just throw if not object. Okay, so if we hyperfind that, okay, I think I need to close down CLion so that it stops screwing with the numbers here. Because, okay, here we go. 791, 790, yeah, okay. Okay, so for the worst case, C++ is still a little bit faster. Let's see, RE, worst case, and then we'll do like an RE best, where we just have like one flag. I guess the best case is no flags. Okay, so this is C++ at 615. And in JavaScript, the best case, 460 something. So in the best case, it's actually quite a bit faster. But it gets worse, or sort of C++ catches up when we have more flags. That's curious. Makes me wonder why. Because I would expect more flags. I mean, it's more work because, right, because we have to do the string concatenations also. So what's the bytecode actually saying? So like we get like hash indices. So this would be a cached get every time, except for the first time. And if we don't have that flag, then we jump to 88, continue here, get global. If we don't have that, continue further down. But if we do have one of these flags, then we do a string concat, tacking on a character. So I guess this part is not optimal. And we could devise more intrinsics for this, especially if we want to write more stuff in JavaScript. You could imagine an intrinsic that represents a string builder, let's say, where you don't want to go character by character and like concatenating JavaScript strings, but rather you would have a string builder that you can give like an ASCII code point or something like that, or a Unicode code point. And it would have an operation at the end where you sort of reify it into a full string. That could be an option. There are definitely some silly jumps here. I see that like it jumps to the very next instruction. After each add, there's a jump to the next instruction. So that could probably be compressed as well. Like, should improve our code generator, or somehow we should figure out that those jumps actually just move to the next instruction and not emit them. That's a thing. What else can we do here? I guess we should profile this thing and see. What is it? XC trace? I think. Oh man, I don't remember the syntax for XC trace. It's like you have to say which kind of profiler you want to use. Time profiler, is that it? Okay, I'm gonna have to look this up. Oh, it finally actually told us something. XC trace, yada yada yada. Thank you, cookie banners. Very cool. XC run, XC trace, record. Template. Oh, here we go. Okay, so I want to do template, time profiler. Targets stood out. No. Dash dash launch. Is that it? Oh, this is the new instruments. I want the old instruments. Here we go. Okay, let's get a top functions view on this guy. Okay, so this is the worst case. And yeah, it's the add operation. So like string concatenation is 21.5% of the runtime, which is very believable. What are we actually doing in there? We're just creating strings. Right. Yeah, so that's kind of unfortunate. So the way that string concatenation works is we don't actually concatenate them right away, but we concatenate them at a later time when you're trying to use them, like trying to actually look at individual characters. All right, update. So when you concatenate two strings, we invoke the primitive string constructor that takes two strings, this guy right here, and then we create a string that has a left-hand side and a right-hand side, these two things. And a string, this is called a rope string. And a rope string can actually have like sort of recursive hierarchy of rope fiber strings like this. And then we will flatten or resolve the rope at a later time. In this case, though, we might not even actually do it because nobody ever asks to look at that string. Wait, what is going on here, though? Byte string contains. Why is that so heavy? Wait, what? Let me invert that, see who's calling it. Byte string contains. That sounds very silly. Wait, so when we're asking for each of these flags, then they do a contained? Say what now? This was ignore case. Wait, where the heck is that implemented? Oh, it's macro expanded. Okay, sure. Okay, so like when you do dot ignore case on a regex object, we go into this guy right here, and he will fetch the original flags and then do a contains on that. So we do a string contains on it. That's pretty not optimal. Right. So we're doing like linear O of n character search through this string every time that you ask for one of the flags. And it is a hefty chunk of the profile. We should not do that. So let's see. Instead of this, I guess we can just get we can pre-compute this when we create the object, I guess. So creating a regex object, can you set the flags after the fact? I don't think so. Okay, so it has flags. So we could just have like a thing here, like flag flags as bits, bit field or whatever. Flag mask. That works. Okay, and then how do we compute that? Where do we have all those flags, by the way? I keep forgetting where they are. Forward.h. Okay. So what if this thingy, we need to make an enum somewhere. I'm just going to do this. like this, let's say. Okay. Okay. Got a little messy there at the end, but we're good. So we're just prototyping. It doesn't have to be perfect. Let's see. Flag mask. So when I create this guy, I just want to, I'll just do it right here. Just iterate over the flags, and yeah, exactly. We're just gonna do this just to see if we can knock a bunch of it off. And then instead, when we're extracting it, instead of doing it contains, we're just gonna ask for the flag mask. And we'll say like flag mask amp regexp object flags. Then we need the name of the flag name that's being passed to the enumerate function here. Not quite. Use of undeclared identifier flag mask. Okay. Oh, right. Flags. And I have to U32 cast it. Oh my goodness. Okay, now we're definitely getting faster. So 399. Let's test this in C++. I mean, now it's not fair to compare because I don't have this fix. So just make a hack branch here. And we will commit some of these fixes, even though they're very hackish. They will be things to clean up at some point. Don't contains in regex flag accessor functions. Yeah. These are not final commits. As I keep saying, we are just hacking around to see what we can discover. I just want to test this out so that we can see how it affects the runtime. Okay, so this is C++ with the flag fix to not do string contains. So like 548 in the worst case. Right? This is the C++ version, right? So 548 was a good one. And the JavaScript version, worst case, 402. Ooh, okay, so now we are actually cooking here. We're substantially better in JavaScript with that knocked out of the profile. That's great. I don't have a solid explanation for why that makes JavaScript catch up and go faster, but I'm glad that it does. Maybe there's a reason why that makes sense. It's not intuitively obvious to me. Would be something to dig into as well. Oh yeah, so it's clearly the JavaScript version is now beating the C++ version, like with flying colors, right? Substantially faster in the worst case. And the best case, with a single one in C++, it's like the same speed as the what best and the worst case are the same speed in C++. It's kind of interesting. 402. Best and the worst case are the same speed in both versions now? Okay, well, let's do another trace. Of the worst case, because it's interesting. Oh, wrong instruments again. I forgot. Because the new version of instruments doesn't have top functions, which I love using. Okay, so here we no longer have those string contains, which is really cool. In fact, what are we seeing here? It's like the overhead of the function calls is basically it. Dynamic cast. Okay, so there are like some little things that we could probably poke at, but this is looking really, really good at this point. So that's a substantial improvement from where it started, right? And yes, the fix to the flag getters to not do string contains is doing heavy lifting here, but the porting of the flags getter to JavaScript is also adding more performance. So it does seem like this could be a promising thing to be doing. Right, just timing again here, best and worst. Why are they the same? I don't know why they are the same, but that's interesting. Maybe because it doesn't matter anymore. Oh, wait. The worst one was a lot worse when we were scanning the string over and over. That's why it was worse. It wasn't worse because of the string concatenation. It was worse because of the scan. Of course. So, right. So once you eliminate that, then there's not much difference between the two. Because string concatenation is actually not particularly expensive, which makes more sense with how the world should work. Like string concatenation is a GC allocation where you're storing 2 pointers for the left and the right side of the rope string, and then you go about your day. There's no actual concatenation happening, which is why it's fast. So as long as you don't incur a garbage collection cycle or a garbage collection, then it should be very fast. Oh shoot, did I think I accidentally unstashed something I didn't mean to here. So these were the JavaScript versions. And the C++ version is much slower than the JavaScript version in both cases. That is... Well, that's kind of great news, actually. So yeah, so I think this is definitely something to move forward on. And there are, like we already saw in the bytecode, that there are things that we're doing that are not great, which we could do better. Like we had all these jumps here to the next instruction. They should totally just be disappeared somehow. And the string concats, if they do become a problem in the future, we can devise some sort of intrinsic for string builder. But if they are not a big problem, then we can also just leave them like this for now, because that's also an option. Yeah, I mean, this is pretty sweet. You also have 2 returns here, could probably be consolidated. Yeah. Okay. Anyway, so all of this to say, or all of this, the whole point that we did this was to make the flags thing faster, because I cared about it, because it was in the WPT test. And I wonder how much faster it got for that thing. So do I have this guy right here? So let's, oh wait, I would have to rebuild everything. Anyway, we've seen in isolation that it was a very helpful optimization. So I think we're good here, and I'm not going to package this up today because I just wanted to do the exploration. I think it needs more refinement, and we need to figure out how to integrate it in the build system. I need to figure out how to have more than one function in the same JS file. I don't want to have these inline strings in the CPP file, obviously, with JavaScript. They should be in separate files like I originally did it. So we do need some build system stuff for that. But this does seem like a really interesting path forward, because, on the same track that we are adopting Swift to be a safe language, JavaScript is also a safe language that we already support in the code base. So this is sort of an interesting parallel way to make parts of the code safe as well by doing them in JavaScript. And especially if it makes it faster, then it's a no-brainer, right? So, fruitful exploration, I would say. And I think we're going to end the video here. So if you made it this far, thank you for watching, for hanging out. I hope that you saw something interesting, and I certainly found this to be very interesting. And I'm going to try to refine this and figure out how we want to move forward with it. But cool results, I would say. So thanks for hanging out. I will see you next time. Bye-bye.